the workshop who will give the colloquium today, Jörg Schmalian from Karlsruhe Institute of Technology. Jörg got his PhD in the Freie University of Berlin. He was then a lecturer at Oxford, a professor in Iowa State University and Ames Lab, and since 2011 has been at the Karlsruhe Institute of Technology, where he's also the head of the Institute for Condensed Matter Theory. Jörg is very well known in the community of quantum materials and superconductivity. He's an APS fellow. He won the very prestigious Bardeen Prize for superconductivity, and also the Physics Prize from Dresden. As I said, he's known for having worked on a lot of different superconductors, and in particular, he has been working on a new frontier in unconventional superconductivity, which is the connection with ADS-CFT-inspired ideas that have been applied in condensed matter. So we hope it's been very fruitful, this area, with the connections between high energy and condensed matter. And we're all excited to hear Jörg. Welcome, and thank you very much.
Yes, thank you very much. Thanks, Rafael. Yeah, it's a privilege to be here. Thanks for having me. We have had an absolutely wonderful week already, almost 3 days. Wonderful number of days with wonderful talks where I learned so much. Today, I want to tell you a little story about condensed matter theorists' perspective of a fascinating topic, namely the holographic description of certain scale-invariant quantum mechanical systems. Before I go there, I need to mention the wonderful list of collaborators I've had the fortune to interact with. There's Ile Estelis, who's actually here in the room, with whom everything started a number of years ago in 2019 when I happened to be on a visit at Stanford, and we just hooked up. Konrad Skarm, who was at Leiden, Gian-Andrea Inkov, Veronika Stangier, and Davide Valentinez, who were postdocs and students in Karlsruhe, and Daniel Chi at Louisiana. And initially, this work was supported by the Moore Foundation when I went to California, and currently we receive funding from Germany and from the Simons Foundation. Very well. So this will be about emergent geometries. So let's start with the problem that many of us in the condensed matter context understand. Namely, we have, say, some excitations, single particle excitations characterized by quantum numbers. And these objects are interacting by a two-body interaction. And we are trying hard to calculate those two-body interactions. We are summing diagrams. We are looking at scattering theory. And in the end of the day, this is an understandable problem, and we will get some insights. And my analogy in the context of playing chess is that we have mediated by some medium interaction between two players, so we have a two-player chess game to deal with. And this is very naturally characterized by a flat space. But imagine you would want to play chess with at least 10 players, and you need to arrange your game board in an appropriate way. What will actually end up happening is that you will put a lot more emphasis onto the circumference, on the boundary of your game, because that's where your players are sitting and want to interact with. And at least to the participants of this workshop who were in Tobias Mikler's talk, I believe yesterday, they will recognize that this is one of the representations of an hyperbolic space, of a space that has on its circumference almost as much weight as it has in its volume altogether. So this is something I just stole from Rolf Wolfram, because you can just make these nice pictures. It gives you an idea what's happening. What's really cool is that you can, like usually in mathematics, then go, that's just like the gamma function for negative arguments. We can ask, what is the single-player chess game? And that's what you can see here. It must be incredibly boring, but I've still felt I should not deprive you of that option as well. But we will be more interested in this regime. So what we will be doing, basically, is that we will try to see what would be, say, the natural analog of the two-body scattering problem. that corresponds, if you wish so, to a many-body interaction where almost everybody interacts with everybody else, where you cannot identify individual players even as their unique excitations, and where the integrity of, say, quasi-chess player will just be wiped out. So maybe my caricature for this one is just something where you would just lose the integrity of individual quantum excitations. Good. Now, what will we do in this talk? We will look at models that we can solve. I'm a theoretical physicist. I love to hide in a corner and do calculations at length and find this very soothing. And so we will try to find models that we can solve where, as we increase in one way or another the strength of interactions, decrease the temperature, whatever you wish to say, and where you start off in a description where clearly individual bosonic or fermionic excitations are governing the properties of a system, where they start increasingly coupled to one another and maybe give rise to collective excitations. But in the end of the day, we will get what one might call, from the perspective of the individual particles, a soup of no structure. And this seems like a hopeless endeavor, and it might just be something that is, say, has no substantive, interesting information in it. And what we will see is that for certain problems that we can solve under certain conditions, what we will find is that the system is very naturally described by a geometric formulation where we will live in one extra dimension compared to space and time. We will have space and time and something else. And where we will see that there's a certain hyperbolic geometry, we will even see that there will be black holes emerging, where will be atmospheres of order parameter excitations around that black hole, and that we can describe all of these things in a rather natural way. So now, this is completely old stuff for people who are working in the holographic community. That's what's been done since the late 80s, pioneered by Juan Maldacena, Witten, and so forth in this context. My perspective, this little additional edge that we will be giving to this perspective is that we will be, just like good old-fashioned solid-state physics, start from a Hamiltonian. There's a boson, there's a fermion, they couple to one another, and then we will work our way through, and all of a sudden, there's a black hole there. So I did this not so much to teach to the holographic community how they have to look at their problem, but this was entirely therapy for myself. While I was just sitting in too many talks where I didn't understand a word, they all looked really, really cool, but still I didn't understand it. So we felt that it makes sense if we can find models and formulations where we achieve this type of insight from our own perspective, and maybe even give something back, give a perspective, an aspect of it back that might be of interest to other communities as well. So this will be this talk as we will progressing. So how do we do this? Well, I work on superconductivity, so why not make our atmosphere around the black hole made of Cooper pairs of a superconductor? Superconductivity is, as far as I'm concerned, the coolest state there is. You can lift up Master Yoda. You can, well, find obvious joy in looking at superconducting levitation. So what's wrong with looking at this state in order to understand some of these perspectives of, say, holography and quantum criticality and superconductivity that is not even made of quasiparticles? So one example I will be giving you will be even a situation where if the quasiparticles are well-defined, we don't find superconductivity. We only find it because they are in one way or another sick and ill-defined, which is, I think, rather cute. Well, a word about superconductivity. This is a colloquium. Well, we've all heard of it. There is electrical resistivity dropping to zero below a certain unmeasurable, to an unmeasurably small value below at a critical temperature. Here you see yttrium barium copper oxide, one of the high DC cuprate-based superconductors. The stuff levitates, as we've seen, Master Yoda, you can essentially understand, and this was, of course, the key insight originally from giants like Fritz London, Ginzburg and Landau, Bardeen, Cooper and Schrieffer, and maybe C and Yang, where we understand that this is a state of macroscopic quantum coherence. So from the perspective of an atom that is, or an electron that is in an atom, what happens to the superconductor is entirely boring and ordinary. It's just surprising that you can fill a bucket with this stuff and touch it on a human length scale. And therefore, among others, you see that you have macroscopic quantum effects, you have flux quantization, you can build a qubit out of this in a quantum computer if you really want to, and so forth. And there are interesting optical properties in the infrared and so forth that you can use to build metamaterials out of. So that's the superconductor we want to talk about. If I look at the periodic table, those are just the elements, not even the binaries, ternaries, quaternaries. A significant portion of them will become superconducting. Some of them, like calcium really, or sulfur, really only under pressure, but they do. So, and we will see, and we will go over this in a few steps, just because we need to get familiarized with the properties of superconductors. We will see superconductivity is the absolutely normal, to be expected state of any decent metal. If you've got a metal, if it's not too dirty, it ought to be a superconductor eventually. So this is not the exception, this is the rule. And that's what makes this, it's a macroscopic quantum effect, and it's inevitable. I mean, how much cooler does this get? So this is my perspective of the good metal. The understanding, the theoretical understanding why metals can be captured in a theoretically transparent language ultimately goes back to Lev Davidovich Landau in the late 50s, and who realized if I have a conglomerate of electrons that may interact in some rather complicated way, ultimately what will happen is that the excitations above the ground state can be counted by simply looking at quantum numbers that are adiabatically connected to those of an ideal gas. This is cool. It's a very, very complicated system, but the phase-space constraints that are at play, of which I have no time to get into, are of a type that ultimately what you see is, say, a single particle momentum, maybe a spin of an electron that has a little two-particle scattering matrix element, maybe with another single particle state with a different momentum, maybe a different spin. And it goes so far that you can basically ignore the entire integrity of what's happening behind all of this and just look at two-particle scattering events. And then you understand this Fermi liquid, you understand the metal. What you get at the end of the day might be effective masses and so forth that we will see. These effective masses may be 1,000 times that of the electron. But still, it's just a mass. I mean, and nothing else. So this is a really cool thing. I mean, Sentel, one of our colleagues, who was one of the more eloquent ones, put it very nicely. A Fermi liquid theory is basically a theory that was supposed to be written down in the 21st century, and just by accident, and the pure genius of Landau was written down in the 20th century, and that's why we have such a hard time understanding it, right? So, because if you read the original paper, I had to go through at least 6 attempts to even get an understanding of it, and then you get maybe to some idea. So what is, in the more mathematical formulation, the exact ground state of such a metallic state? Suppose we're ignoring superconductivity for the moment, the exact ground state has a finite overlap to some non-interacting electron wave function. And this finite overlap, we call it the quasi-particle weight, tells us that the electron remains a good quasi-particle. It may have a cloud of stuff around it that it drags on as it moves, but ultimately it's a good quasi-particle. It acquires an effective mass, I mentioned this already. Its lifetime is long, parametrically long compared to its excitation energy, which is why it keeps its integrity. This is a good metal. Now, once we have established that the quantum numbers of the normal state are understood, we can ask the next question, well, how about superconductivity? And it will turn out that these insights, in particular the finite overlap between, say, the exact wave function and the wave function of some non-interacting electron system, is crucial for this inevitability of superconductivity in a good metal? Well, here are a few observables. So these effective masses, these effective scattering matrix elements, these effective lifetimes, they all have measurable implications, of course, if you look at charge responses, just the specific heat, temperature dependence, or the electrical resistivity. But if you now look for superconductivity, this is my one-slide summary of the conventional theory of superconductivity. If you look at superconductivity, yes, we start with this finite quasi-particle weight and only 2 particle scattering events. And then you can ask for an ideal gas, what is the response of a 2 pairs of electrons, or pair of electrons, propagating in free space without any other interactions? And you will find there's a log here. So this is the particle-particle response of an electron with a Fermi surface, with Pauli principle at work, and the finite quasi-particle weight, and you find that there's a log. And if you now add to this problem some interaction that wants to bind electrons in some channel, let's be easy, let's say these are electrons that couple to lattice vibrations or something like this, that gives an effective attractive interaction. You can sum up a geometric series. You can argue that this is the dominant diagrams that you should be summing up. You find there's a divergence because this fellow here is, no matter how small this coupling is, the log will always be at some point sufficiently large to cause a divergence of a response function, and hence you have an instability, and hence you find superconductivity. You find a result for the transition temperature with this essential singularity, and that's, in its nutshell, the instability that was pointed out and led to the theory of Bardi and Cooper-Schrieffer that's now understood to be the theory of superconductivity. Good. What we needed for this to work was that we had good quasi-particles. If we didn't have this, the coefficient here, for example, would be 0. Well, then there's no logs. This would be a constant, and there's no fun anymore, right? So therefore, this was crucial. The properties of the state that is the normal state out of which the superconductor is born is incredibly important to make the superconductivity eventually happening. So what happens if my metal is no longer a good one? This is ultimately where I in this talk, want to go to. Of course, please. Yeah. Yeah. The wiggly lines in the left are some boson that ultimately, some Yukawa coupling, if you wish, so some coupling that couples these electrons to and causes binding. Photon will not do this. Unfortunately, phonons are odd under parity in time reversal, and this will actually make this coefficient here always have the wrong sign, and there will essentially be plus something positive. So you will never get this out of photons. But you can get this out of lattice vibration, so density fluctuations of the ionic lattice. You can also get this with some trickery out of the own magnetic excitations of the electron fluid itself. Yeah. Mm-hmm. Yes. This wiggly line is, could also be a Coulomb. I mean, as I said, this could be a phonon, yes. It could also be a collective excitation of the electronic system itself. So the scattering matrix element ultimately gives rise to certain corrections in the thermodynamic properties of such a compressible Fermi state. It doesn't have to. It could be even a photon, because here it's not important what the sign is. For superconductivity, a photon would not do, unfortunately. I mean, it would be fun if you could shine light on a metal and then it would be superconducting. Yeah. Yes. What a brilliant question. Yes. So in the conventional theory of superconductivity, the transition temperature is a very small scale. As you see, this is exponentially small, right? So this gives you an energy scale. The velocity of the electrons is the Fermi velocity. It's about 1/300th of the speed of light. So out of a velocity and an energy scale, I can find a natural length scale of this problem. If you look at this in a conventional superconductor, you find that this length scale can be very, very large. So of the order of nanometers, 1,000 angstroms, or I would say about 1,000 lattice constant is easily possible. Now that's very surprising, because if we, two of us, form a pair under those conditions, there will be plenty of people in between us, and we will still not lose track of one another, which is, again, super cool. In some of the high-temperature superconductors, the temperatures are higher. Hence, and the velocities are not all that different. So hence, the size of this pair shrinks quite a bit. It is, however, still large enough to conceptually maintain this picture that I've had here. So, and then you can go to an extreme limit, where basically the interactions are so strong and they come so close into each other, and basically the interparticle distance is very large because you have very dilute states. In that extreme limit, you can even make a genuine, well-defined boson out of these electrons. It has no internal structure anymore. The binding energy is too large, and then you have Bose condensation, right? So you can have an entire spectrum. It's a crossover in some situations. There are phase transitions in others. Depends a little bit on details. You're very welcome. Okay, good. Where are we? Yes. So I wanted to ask the question, what happens if the metal is no longer a good one? So we need to find scenarios where metals are no longer good ones. A very nice one that was also much discussed during this set of lectures here is if you have some ordered state. For the sake of argument, it's, for example, possible to imagine some magnetic state behind this, or some state that breaks certain orientational symmetries. There are all kinds of things we can imagine. And then we have a phase transition temperature where we heat the system up, and then we lose the same magnetic order. And what we can do is, and what we means our experimental colleagues who actually are standing in the lab doing the real work, what they can do is to tune knobs, such as applying external pressure, pulling the sample in a certain way, apply magnetic fields or the likes. And in those cases, we can destroy that order because quantum fluctuations get, for one reason or another, increasingly large. And then we need to ask the question of what happens at a phase transition, where quantum fluctuations can, under no circumstances, be ignored. And this goes under the name of quantum critical states. Now, what happens there? I will give you the caricature version of it, but that will be very useful for how we do this. What happens is there's no well-defined mass anymore. The mass is a scale invariant quantity that ultimately diverges. The scattering rate is no longer long compared to the excitation energy. It's parametrically the same. So we can no longer say this is a well-defined particle. It looks like a blip, but if you look at its spectrum, but it is just an object that is as likely to decay as it is to exist. So therefore, we call it a no quasi-particle state anymore. And what we find is our quasi-particle weight disappears as well, with some power law typically and so forth. So we wish basically to ruin the beauty of what Landau has achieved. Because of these strong quantum fluctuations, this is possible at these phase transitions. And in its vicinity, where we have an energy scale that controls this, we wish to ruin all of this and see what happens. So let's do a toy calculation just to get a sense for the problem. Let's sum up the same diagrams. All what we do is we say, well, the coefficient of the log is gone, and therefore the next leading term is a constant. This response is a constant. And then we repeat everything as is. We have some contact interaction that stands for this wiggly line here. It has basically not much internal dynamical structure, otherwise I couldn't do this. And then I get the same result, and now all of a sudden, this no longer grows as the temperature is decreased, so therefore this will not diverge, and therefore I only get superconductivity in the exceptional situation of a very strong interaction. Now for the condensed matter people in the audience, this is what we know to be the reason for itinerant ferromagnetism. Ferromagnetism, iron, cobalt, nickel, that we stick to our fridges to see nice pictures. This is also a wonderful quantum state of matter, but it actually happens as an exception. You need to exceed a threshold coupling in order to get to such a state. And then it's an exception. It's good to have ferromagnets. There's nothing wrong with ferromagnets, but they are not the natural norm. They are not the inevitable state, because you need a threshold coupling to achieve it. If this was the case, once we have ruined the quasi-particles, we would expect no superconductivity or superconductivity to be weakened. That's the important insight here. So it therefore makes on occasion sense to check whether this wonderful theory is in compliance with the experimental observations. And so superconductivity should be the exception is the statement. And here we have a couple of examples. We have here a material that is cerium, palladium to silicon 2, which is a so-called heavy fermion superconductor, a material that orders magnetically, but also in its non-magnetic state has a much enhanced effective mass of several hundred electron masses. If you suppress the magnetic ordering temperature, you find near the disappearance of this ordering a strong fluctuation regime, you find anomalous lifetimes effect, and you find superconductivity. You actually only find it there where it's not supposed to happen. This is ill-behaving nature. You have the same situation in cerium indium-3, a related material with a similar behavior. This is a completely different material. This is an organic charge transfer salt. You have a rather different magnetic state. We have funny different lifetime phenomena here in this regime where it's governed by fluctuations, and we see that there's superconductivity right where the quantum fluctuations are strongest. And last but not least, iron-based superconductors, these have been discovered in, I think, 2009, have captured quite the attention of a large part of our community, many of us here. And again, we have some materials where there's evidence for some sort of criticality, and this is where the transition temperature is the largest. So all of these materials are misbehaving with regards to the theory I've just pointed out to you. We need to figure out what's going on. Why is superconductivity in critical metals, in metals that are poorly defined, so abundant? That's what triggered all these considerations that we want to look at now. So how do I describe a superconductor in such a scale-invariant critical state? There are many proposals. I want to point out one to you that came not from the condensed matter community, but that has its roots, and I mentioned it already, in Maldacena, Gupsa, Klebanov, Polyakov, Witten, all the giants of the particle physics and string theory community. There is a early on important work pioneered by Damson and Subir Sachdev and collaborators on how to apply this in the context of condensed matter systems. And so what's the story? What we do when we do quantum field theory of condensed matter systems, we really want to know the partition function of some d+1 dimensional quantum field theory. D stands for spatial dimensions. 1 is the time. We have to look at dynamics, quantum dynamics, d+1. That's more or less what many people would be doing. The formal way to write this is why we have to just sum over all quantum states, have some Hamiltonian, and so forth. What these people are told us in some nutshell is, well, there's an extra dimension. This extra dimension is something we need to discuss what it is. But this extra dimension is in addition to space and time. And if you solve a problem in this extra dimensional situation and add to it gravity, which I indicate here by these curved lines, which are the negative curvature of space involved, then you get this statistical mechanics of the quantum field theory, and under certain conditions, you can do a simple quasi-classical calculation for this gravity problem that gives you information about the quantum problem that you wish to solve in the first place. This is super cool, right? And this is where I got all these, I mean, the community was talking about this, had significant excitement, and that's what we want to understand. So the state, the space here, that's this gravitational space, is so-called anti-de Sitter space, which is basically a hyperbolic space in some, see under what conditions it's hyperbolic, and it's a space of negative curvature. Good. So this was the answer. Lots of application followed. You can look at transport where quasi-particles are no longer defined. There was a bound given for the shear viscosity of quantum fluids. Superconductivity was discussed by the late Steve Gupsa and Hotnell, Herzog, and Horowitz. Charge density waves were discussed. Non-equilibrium dynamics was analyzed within this framework for systems where we ordinarily wouldn't have the tools to describe those. So that was quite exciting. Because I need to talk a little bit about gravity, I just want to at least set the language and give you my 30-second summary of general relativity. Which is basically, well, there might be black holes and there might be stuff like lensing where gravity influences other particles. So, well, the easiest way to understand, of course, the Einstein equations is to write down the Einstein-Hilbert action. which is all governed by an appropriate metric of the curved space. There's here this cosmological constant that we will have to discuss a little bit, and then the Euler-Lagrange equation just gives you the Einstein equation. Well, that's good. So therefore, we at least know there's a stationary principle, and it's just more indices, and it's a bit more annoying, but we have Mathematica. Then you can ask for metaparticles that are exposed to this gravitational field, have their own theory and their own dynamics. We will look at metaparticles exposed to a gravitational field. There is some energy related to this. This energy is, of course, the source of the gravitational field theory, and that's what we've got to do. That's, in a nutshell, all what you have to do. It's just like electrodynamics, right? This plays the role of the charges, and this plays the role of the electromagnetic fields. This cosmological constant can be positive, negative, or zero, and if it's negative, then we are in this anti-de Sitter space that we want to look at. One way to understand why it's probably anti-de Sitter makes sense, if you calculate the heat capacity of a black hole, it's at least positive for an anti-de Sitter space, which is not all that bad. Heat capacities that are negative make me mildly nervous, so this is one of the many reasons why this is a good way to describe a system. So now we will understand by looking at it. This is the anti-de Sitter space 2. Under one condition, namely that I do what statistical mechanicians always like to do, namely to look at this in imaginary time, because this is how you determine the statistical mechanics properties, and how also Stephen Hawking told us you have to easily look at, say, cusp singularities and so forth. So the Euclidean version of this anti-de Sitter space is nothing but a hyperbolic space. So what we have is in 3-dimensional, we have a constraint that fixes the surface, and that's a constraint here, x1 squared plus x2 squared minus x3 squared is -1. This defines us this hyperboloid. What we need for this talk to make some, say, more quantitative statement is, what are the geodesics on this curved space? And this is very easy in this parametrization. The geodesics are these red lines here. They are the intersection of a plane characterized by a normal vector. The plane has to go to the origin, as you see here, and this red line is therefore the geodesics in this parametrization. So, and this will play a role. What we will see is that the space of geodesics is basically just the space of these vectors. So therefore, and in order to even have an intersection between a cone and a space, the slope has to be of the right nature, because you don't always cut to a cone. This gives you this condition here, and therefore this defines a certain subspace of R3, and this is the space of geodesics. What I will convince you of, and I don't know whether it was all that clear, and if there are experts in the room, they should correct me, to the holographic community, we live in the space of geodesics of ADS. So that's what I want to convince you of. We are not actually living in ADS. We are living in the space of the geodesics. Okay, that's why I'm torturing you with this nonsense here. So we have seen this parametrization. This is some hyperboloid. It's always good to find a parametrization that guarantees that this is fulfilled, and I'm giving you one here. This essentially goes back to so-called Poincaré's half plane. So these are two parameters that once you insert it, you square them up, you check, you cover exactly this hyperboloid. And in these coordinates, the anti-de Sitter space looks like this. There's 1 and 2 coordinates. 1 goes from -infinity to +infinity, will be our time. And this will be our extra dimension that we need to understand what it really means. And if this is the induced metric in this language, then we can also ask the question, what's the induced metric of the space of geodesics? I can equally parameterize it by something else, and you see it's a different space, has a different curvature, has a different metric, right? So the geodesic space is not the original space. It's just, I mean, it's important to look at these little details here. What we will see is, and the geodesics drawn in this parameterization are semicircles. There's an easy way to see that this matrix must give you these curved geodesics. So if I say I'm starting here at zeta equals 0, and I want to go here, then, I mean, if it was flat space, I would just go like this, right, along the axis. That's the shortest way. But with this matrix, I see that distances for small zeta are infinite. So I really better dive into the bulk, because this is where short distances are much shorter, because there's this denominator here, but this is larger, that the distance gets smaller. But I need to get back, because that was my assignment, so therefore I have these semicircles. Okay, good. Now we know everything there is to know about de Sitter spaces, right? That's just all there is. So we can generalize this, and we have spent some time with our student Veronica Stangier on all of this. We can look at the, I mean, this is of course all known here. This is the Euclidean de Sitter space in higher dimensions, can be parameterized. And we again see that there's a related matter where formerly there was a time, there's no time and space. And you also see at fixed zeta, this is basically flat. The curvature is only in this one direction. You can build a Laplacian, you can calculate, you can have fun in this space. But you can also go to the space of geodesics and have your fun there. And there you again find that you find different metrics, you find different distances, and you find your own Laplacian and your own properties. Now, we're almost done with this little excursion into differential geometry, but it will be useful for our conversation as it moves on. So you want to ask, can I connect between these two? Because I told you this is where we live. This is where the calculation is possible and easy. And there's an actual connection that goes under the name of radon transformation. So if you've ever been in an X-ray tomography, then the image that's been obtained there was actually reproduced by performing what goes under the name of an inverse radon transformation. So you average over certain planes, which are the planes which you, from the direction of the X-ray beam, goes through your body, and therefore you live in certain space, you average over certain planes, and then you get a function that depends on the parameterization of the planes. And now there comes a cool property that rescues all of us, namely, if I apply the Laplacian in the space of geodesics, it's the same as applying the Laplacian in the space, in the de Sitter space, and then do the radon transformation. So therefore, we can communicate with these spaces in a very, very efficient way, and this was the key insight for us to make this connection and to derive holography. Good. So I think I'm slowly coming back to less formula-heavy conversation here. The fact that these geodesics are important is also been discussed in a rather different context. So if you have in our actual space, so X and Y, no time, fixed time, and I want to know, for example, the entanglement entropy. We just had a wonderful talk on entanglement entropy of, say, a region that I'm carving out, and I'm asking what is the entanglement of this region with its surrounding. Then you can find, if I happen to have some holographic mapping that I want to get to you, that basically the surface area of this geodesics, as it goes into the bulk, tells us what the entanglement entropy of the problem is. This is a very famous statement from Ryo and Takayanagi. So therefore, these descriptions of looking at problems in geodesic perspectives is very crucial to capture in an appropriate way entanglement. In my personal view, this is why gravity is important. Not because there's something massive here in the literal sense of gravity, but it's because it's a natural way to describe the entanglement that you have at the quantum critical point. So how do we do this? Now we are coming back to our condensed matter perspective. I look at fermions. They are either compressible or Dirac fermions. I will look at both. We will have some critical boson that if it condenses were to give us this ordered state. This could be something that describes a magnet, could be something that describes a so-called nematic or an orientationally ordered system, and that intercouples with a U-Carver coupling. Now this problem is unfortunately not solvable, so I need to make it solvable. And what we will do is we will include then more than one fermion. We will have n fermion flavors and m boson flavors, and we will randomize this coupling constant. And then we find a way to solve these problems in large n limits, which is something I will completely brush under the carpet, and everybody who wants to discuss this with you and argue with me about it should do so, but I'm not going to do it now. And there's one important thing when you then describe the system. This is an insight that at least we have learned from the spin glass community. You'd actually, the characteristic variable that describes excitations in the system are, this is dead now, right? Yeah, but there was another one, right? Does anybody have some? just the good old-fashioned optics one? Green. Green is good. I'm fine. Oh, there's no battery. It has to be charged. Yeah. That's, yeah, I think it has, we will be fine. Okay. Yes, so this problem, so we look at the fluctuating variables are actually correlation function, which is just useful for us to keep in mind in this specific large N limit. So we look at fluctuations where we have fermions that correlate or that form pairs and bosons that are scalar bosons that run around and so forth. So here comes a model that we managed to solve that gives us all the desired properties of lifetimes, mass divergences, and actually pairing interactions that are all highly singular with power laws. That's the work we did with Ilya in a number of years ago, and it's basically a zero-dimensional problem. It's, if you want, so a quantum dot with lots of excitations in it. It goes under the name of Sachev-Yekitaev models that were very popular in order to describe such non-Fermi liquid states. We did basically a version of that model where we have fermions that couple to bosons with these interactions, and we could solve that in some large N limit and find all of those results. Why did we look at this problem? Because it gave us superconductivity. These bosons mediated the pairing interaction. The red curve is the superconducting transition temperature as function of some coupling constant in some appropriate units, and we could find some critical state that has all these properties, and it gives us a superconductor. So what we had there was what we needed to have to describe, have at least a caricature of a non-Fermi liquid state. Now we could ask the question, what is the proper mathematical modeling of this one? The easiest is that we looked at Gaussian fluctuations of superconducting excitations near the onset of this superconducting instability here. So it's just some Gaussian theory, and all what I want you to take away is this is awfully complicated. There's some kernel that is highly singular because of all the power law behavior in the problem, and I didn't know what to do with this. You can write it down. These are the lifetimes that diverge with power laws. This is some pairing interaction that drives the system to superconductivity that goes with the power law. It's very complicated, and it's not something I could do much about. But then we realized that the good old-fashioned theory of superconductivity had this logarithm here. I'm just rewriting it again. And you can see what actually happens with this linearized superconducting gap equation in this non-Fermi liquid state. And what you find is it's a funny integral equation that was discussed much in the community by pioneers like Andrei Chubukov and Artyom Abanov. So this is an integral equation that gives us the superconducting instability, governed by all these power laws. Here we see that this is not a Fermi liquid because of all these sick power laws. And with a few steps, you can transform it into a differential equation. You find that with a little bit of change of variables, that this integral equation has the same properties than the Klein-Gordon equation in either this hyperbolic space or in this space of geodesics. We couldn't tell the difference because this was only depending on one variable. Time was not varying here. So this is not so important except for the fact it gave us a clue what to do. We had an idea how you can interpret the additional dimension that is basically inverse energy of probing some internal structure, and we could then try to solve it, and this is where this maybe becomes more important. So we have pairing excitations of two pairs that you inject in the system at different times, and this depends on not, even though there's only one variable, time. This excitation has two coordinates because it has two time variables. It has either the center of gravity time, which is the total time that you measure in non-equilibrium dynamics situations, and it has the relative time, which tells us the internal structure of the Cooper pair. So you have, just like when we have two masses, there's a center of gravity motion and a relative motion. Here we have the center of gravity time, which tells us something about non-equilibrium dynamics of the entire system as a whole, and of the internal excitations that you can make, because the Cooper pair is not all that tightly bound. It has structure. And we need to worry about this internal structure, and that's why we need an extra dimension. And that's ultimately why this holography stuff works. Yes?
I have a question. I don't understand why this lifetime
Mhm.
So now we are with lifetime tau.
Yeah.
And it's the same as the first part.
You can do, this is a function that's a correlation function, it depends on time. You can do this for any system. There's nothing special about applying this. You can apply this to a good old-fashioned BCS superconductor. Important is, in a good old-fashioned BCS superconductor, this axis is ultimately not all that important. There's a bound state energy, and on the scale of the bound state energy, the system is structureless. There are some wiggles where people wrote important papers about, but that's not fundamentally important. So important is not the existence of this variable, but the importance that you cannot ignore it any longer, while you could in the conventional theory of superconductivity. That's ultimately the answer, but of course I completely appreciate that there's so many things that, well, we're understanding conventional superconductors that I'm just quickly brushing over here because I want to focus on something else. So what is so important is if you look at this funny Gaussian action that I just gave you, it turns out it lives in a curved space and it has exactly the geometric of the space of geodesics. So that's just comes from this transformation that I've just shown that we more or less guessed. And then after a while, you realize that this is happening. And if you then do something very similar, you take this awkward expression, you do our radon transformation, which we are now very familiar with, where we average over these geodesics. You can rewrite this in several lines, and what you get is exactly what the holographic community gave us. Namely, that we have a Ginzburg-Landau theory of a scalar particle that lives in one extra dimension and is governed by this funny anti-de Sitter space. So it just comes out of the calculation. It is the natural way to describe the system. And you need an extra dimension because near a quantum critical point where we have these additional quantum fluctuations, the superconducting Cooper pair has internal structure that requires an additional coordinate to be captured. That's how we can reread what we have derived and interpret. That's why we think there has to be an additional dimension, because the object that is formed is a composite, a bound state of two fermions, and it's not a structureless bound state, but it has internal dynamics that is not has a scale invariant structure and needs to be properly treated. You can go further. Now the calculations are a lot longer, but you can do the same thing at finite temperature. Everything I've done here was so far at zero temperature. The calculation takes you several weeks, even if you know exactly what to do. And at the end of the day, you find that the metric changes. It's no longer this metric that I had before. And if you look at this metric, it is exactly what you have when you add a black hole to your system. So basically, this is with the event horizon given by the Bekenstein-Hawking temperature of the system. So what does it mean? Well, if you are at a finite temperature and you still want to look inside the Cooper pair, if your energy is high, it looks like you need to look at the scale invariant properties. Once you hit the scale of the temperature, it becomes structureless again. And this theory tells you to stop looking by putting a black hole there, which I find super cool, regardless of whether this is anywhere useful or not. So, and then you can basically see the event horizon of your black hole, and your Cooper pairs condense basically in the atmosphere of that system. That's how they can be described, and this is how you can get an understanding of superconductivity in these quantum critical systems. We went beyond this because so far I've given you Gaussian theories. We can look at nonlinear effects when this expansion, for everybody who looks into Ginzburg-Landau theories, this is the next term you ought to look at. What happens there is, if you include this, you get feedback. Now you condense and you get a finite expectation value of a superconducting order parameter. So far we have only had it Gaussian fluctuating. Now this object condenses. What happens is, you need to solve the Einstein equation with this condensed object as a source term. You see that the metric and the geometry changes, and this geometry change is exactly the one that you would be getting in the condensed matter look just by just looking at the opening of a gap in the superconductor. So these two statements, again, map onto one another. So to me, this says this is not an accident. There's some deep structure in the theory that tells us that this formulation is simply the right formulation you want to employ when you have a quantum critical superconductor. You shouldn't be doing this in the good old-fashioned way. You need to look inside the Cooper pair that requires an extra dimension and so forth. The last comments I want to make is how we extend this. This was for a zero-dimensional problem. We had only time and extra dimension, which we have now understood. We have not yet looked at space. So now it would be useful if one could extend this to something relevant. As far as I know, my experimental colleagues typically work in finite dimensional spaces. So therefore, it does make some sense to worry about this. So I want to give you two examples. One is a Dirac system, where we are near a mass generating point and a compressible Fermi liquid. And I want to just make this much more briefly now. The steps are actually very much the same. It's just that the technical analogy is a bit more subtle, of course. Here, this is a Dirac system. We have Dirac fermions. They couple to some Yukawa coupling to some bosonic system. And this is actually a generalization of our little Yukawa SYK model that was put forward by Kim, Altman, and Kao at Berkeley 2 years or so after we did our work. And it's a wonderful theory because they already showed that the same large N theory that we employed can be generalized to these Dirac systems. And in this case, what you find is that the fermion and the boson acquire what goes in the name of anomalous dimensions. So they acquire power laws that are unconventional, and they are typically hard to calculate. And this is a way to calculate them. You find here, if you count the number of bosons and fermions, you get this anomalous dimension. You can calculate it in some well-defined way. So we have control over the lack of quasi-particleness of the problem in this Dirac system. And this critical point where this happens is the so-called Gros Nouveau point. That's the point where these bosons open a gap. Now, that's an interesting one because we have a material now at our disposition with so-called twisted bilayer graphene, where we take two graphene sheets, we twist them relative to one another, and we get Dirac cones that, however, are exposed to a very small typical velocity, and therefore the interactions become relative to it much, much larger. And we can play with twist angles by changing the magnitude of interaction. So we can actually tune the parameters in a very, very elegant way. And so if you, and this is here some very recent work in this twisted bilayer graphene at a certain filling, this is the non-interacting electron. You can change basically bandwidths and therefore the relative importance of interactions. You see these Dirac cones here. If you include interactions, these are quantum Monte Carlo calculations, you see there's an opening of a gap. At these Dirac points, they don't give a point in between, but in between there's a gap opening. This is a gap opening because of the fluctuations of a collective boson. We even know what this boson is, at least in the theory. This is a time reversal symmetry breaking, inversion symmetry breaking boson that goes under the name of Kramer's intervalley coherent insulator. It is basically the fluxes that orient themselves on a lattice in a well-defined fashion, and here we see at what twist angle and what dielectric constant of the material you find the transition. So what do we find? We find that the system becomes superconducting whenever the system is sufficiently non-Fermi liquid. At this critical point, the system is not a superconductor if it's a well-defined Fermi liquid. Once it becomes a sufficiently ill-defined Fermi liquid, we find it to be a superconductor. And this superconductor then is described not by ADS2, but by ADS4, because we're sitting in two space dimensions, one time dimension, one extra dimension, and otherwise everything goes over as well, and we need to do a radon transformation and the text, and I've tortured you with this enough. But this copy-pastes over rather naturally to a very relevant situation where we now predict that at this twist angle, there should at least be enhanced superconducting fluctuations, maybe even a superconducting ground state, near the onset of this mass opening. Very weird state of matter. And the last slide I want to give to a work that Ilya Estelis and Sachdev, Guo, and Patel pioneered, where we looked at compressible system with a Fermi surface, went to a critical point, and then found certain power laws that characterize its critical point, something that's supported by lots of numerics that is independent on the approximations that we are doing there. We did the same program here for this system, and we find that now this space is basically our good old-fashioned ADS2 and the flat space in the spatial coordinate, and this goes under the name of so-called Reisner-Nordstrom black hole description of that system. So all of these problems can be dealt with using the machinery that I've laid out to you. This is completely useless if you want to look at a conventional superconductor. You want to have a superconductor that's quantum critical and have no well-defined quasiparticles. Then this is the right way of doing this. So maybe to put this in context, Lev Petrovich-Gorkov, one of the real giants in our field, told us how to understand the scalar field that governs a superconductor and what the characteristic charge of that state is. Or what we are claiming is that we can do the same for a system near a quantum critical point, where we have to have an additional dimension in order to describe said superconductor. And maybe with this, I leave you with this picture. We have understood there can be emergent geometry. It is something that results from a good old-fashioned condensed matter analysis. We have electrons, we have bosons, they interact, they couple. We need to do some theoretical trickery to get to this critical states. Once we are there, we now understand why there was this wonderful success of the holographic community to describe these complicated states of matter without well-defined quasiparticles. And maybe this can have some impact of going the next step and using these tools provided by this community to learn something about condensed matter systems. Thank you so much for your attention.
All right, we have time for questions now.
So I apologize, I'm not in the field, but can you say how the isometries of the ADS space act on these quantum critical systems? Is there some?
No.
Okay.
Another try.
Well, it was a good question. I just am not capable of giving you a decent answer.
So Jörg, correct me if I'm wrong. These large N theories, if you don't do anything about them, they have this residual entropy as you go down in temperature.
In the zero-dimensional problem, not in the Dirac problem any longer.
Okay, but in the zero dimension?
There it's, yeah.
And I suppose that the superconductivity that you found is sort of the way to release
it gets
that.
it out, and there's a zero entropy.
Right. So my question is, are there other instabilities to this residual entropy?
But superconductivity, have we ever found something? I don't think so. There could be charge density wave instability. I would have to kind of design the problem to do just that, right? Okay. But it could be, right? Do you have an intuition?
For me as well. I mean, sorry, just whether. So it seems that one feature of these quantum critical systems is that the internal structure of some composite operator becomes important. But we have lots of examples of other bilinears that condense. Yeah. Right.
Yeah, and then I would have a holographic description of a neutral object and so forth. Yeah.
So I have a question about the bilocal field.
Yes.
So in the context of spin glasses, if I remember correctly, the second time scale basically governs the relaxational dynamics that you see on top of things. So my question is really, do you anticipate different dynamical universality classes that might be imposed through different models? That
yes, very good question. So first of all, in the theory of spin glasses, you need to also insist on taking both time variables into account. You need to do it there because the system falls out of equilibrium. It depends how much you've weighted, since you maybe quenched your system from some high temperature state and so forth. There's memory and so forth. If in this system, there's no real indication that the system will be glassy, but I can still do non-equilibrium dynamics of that system. I can do a quench. I can do Kibble-Zurich mechanisms of nucleations near these critical points. All of these things I can do. Then I would have to do and include and employ this additional dimension. If I don't care about it because I look at the equilibrium properties of a superconductor, I may as well just ignore it. It was important for us to include it systematically in the treatment because Otherwise, we wouldn't have understood the structure of the theory if we didn't know what time is. And it's just irritating if you don't know this. But if you're in equilibrium, we wouldn't need really, because the relevant field configurations may not be important. If you want to have a response function towards, say, an AC Josephson that couples to your superconductor, you, of course, already have to take into account.
Thank you.
More questions?
So I have a question about these extra dimensions at zero temperature. You said
Yes.
it's related to the structure of
Yeah.
the condensate. Can you be more specific?
Yeah.
What is
Yeah.
this extra dimension?
So let's step back a little bit. In the usual interpretation that I've been hearing from the holographic community is that I should interpret this extra dimension as a renormalization group scale, right? And there's nothing wrong with that statement. I have no problems with this. In our formulations, we have matter fields that live on top of in this gravitational space. These matter fields are composites of fermionic degrees of freedom and have therefore internal structure. And the energy scale of that internal excitation, its inverse is essentially, modulus is rather nonsense, so the inverse energy is this extra dimension. So if I probe the system at very low energies, I'm going very deep into the bulk of this extra dimension. If I probe the system at very high energy, because it's the inverse of the energy, I'm near the boundary and surface. So therefore, this intuitive statement of having an RG scale that probes the scale where I'm looking at the system is correct. We just have an explicit expression. So we never need to know anything about RG, we still get the right answer. So it's just how deep you look into the internal dynamics of a composite object of the system.
Yeah, so
Yeah.
I have a feeling maybe similar to what you said at the beginning, like, I feel like all of this is cool, but I'm still very lost. I don't understand. So let me ask you a few questions to just,
Yes.
So this correlation function with 2 times.
Yes.
Usually, in equilibrium, everything depends on a time difference.
That's what we just had as a discussion.
Right,
yeah.
it's similar. So is it sort of that at the critical point, you don't have thermalization, or why?
First of all, at the critical point, so the relative time, which we cannot ignore even in equilibrium, right, is exactly the holographic variable.
Okay.
It's the relative time.
Okay.
The absolute time is just the absolute time. It's just time. So, and if I'm out of equilibrium, I need to worry about it. If I'm in equilibrium, I don't. In either case, I need to look at the internal structure and the additional holographic variable.
Okay. So in equilibrium, is only one.
It's only the holographic variable.
Okay.
Yeah.
Is there some kind of, also, is the gravity theory classical in the end? Is this
Yes.
like a similar to like when you do?
It's classical because
quantum
of the
to
large
classical?
n limit that we employ. If we were to solve that problem at finite n, which we of course cannot, then we would have a theory of quantum gravity. Now the cool part is there is a work by Alex Altland and Alex Kamenev and Dima Bagretz. They looked at the next order corrections, and you can actually do something that at least for the silly ADS2 system would be quantum gravity. But this is going beyond the leading order in some 1 over n. But there's some large n problem that essentially gives us the classical gravity.
There is like this sort of textbook quantum to classical mapping where, take a quantum system in d dimensions, maps to a classical system in 1 extra dimension, basically. Is this a special case of that more general idea?
No,
or this
is different. We are looking at, so we have a d+1 dimensional system that is quantum mechanical because of the extra 1. But this problem is not enough to describe the excitation spectrum of the problem. That's why we need this extra dimension. The gravity there is dynamical, but obeys the Einstein equation of that problem. So in that sense, it is quasi-classical, but it has dynamics. So I don't think it is. It can be captured with this extra dimension, with this d+1. That's not what's happening here.
Let me abuse my powers here to ask you a question. So in the case of the compressible fluid, right? Then I can properly define nodal quasi-particles, like a D wave.
Yes.
How do these nodal quasi-particles, because now you have this extra matter field, if you wish, right? How does it enter in all of this?
Yeah, very good point. So you would, if I told you I have a correlation function that depends on 2 time variables, and that's I go from, so in addition to time, I have actually 2 variables. Now think naively, we have now space and time. You think you get 2D, not D plus 1, or D plus 1 plus 1, right? So what happens is the relative time in a compressible system is frozen in by KF. And there's a form factor, I had it there, it was way too fast. There's a form factor that tells you this happens to be a triplet or a D-wave nodal state and so forth. And then you have the amplitude of the system that still depends on frequency. And therefore, you don't get twice as many variables. You get still only 1 additional variable, because a system gets frozen in by the presence of a Fermi surface. In the Dirac system, it's essentially the same. There, my holographic variable is the Lorentz invariant relative time. And the total momentum is again frozen in because you have an L equals 2 state on L equals 3. Your pairing state has a fixed angular momentum, and you're freezing in these angular momentum. Very good question.
Repeating what the guy on top said, I was quite. It's a very cool thing, but it's quite complex. I was quite lost. So sorry if I make myself a fool with this question.
Don't be sorry.
But I know very little about the ADS and about superconductivity. But I do know that phase transitions happen when you break symmetry.
Yeah.
And I know that ADS is extremely symmetric space. It's asymmetric as a sphere.
Yes.
So is there any correlation of why you are on the critical field? Like if I try to get away from the critical field, something will happen with the... I just wonder, is there any connection between this maximum symmetry here and break of symmetry here?
This is a sequence of brilliant questions. And if we are at the critical point, the theory has a higher symmetry at low energies than you would naively expect. This is partially responsible for the fact that we can do these type of theories. We are never really, if we go into the ordered state, say a magnetically ordered state, then we would no longer have quantum criticality because the system has gapped out many states. There's a scale. And if I wanted to do the gravity theory of this problem, I would work forever. It's not an easy gravitational space. We are picking where we can, this tiny little window where we can solve the problem, which is near the critical point. It happens to be the one that is hardest with other tools, so therefore it's good. But if I wanted to look at an ordered magnetic state with a scale, well, you know what you do? You just do your good old-fashioned condensed matter physics and look at a gapped state in an effective mean field theory and solve it this way. You don't do this. This is foolish once you have additional scales and lower symmetries. But one caveat I can make, in the compressible state, we actually broke the symmetry. It was not an de Sitter space. Space coordinates and time variables are very different because the Fermi surface makes a big difference between excitations in energy and length scale excitations. So there was a lower symmetry, but still dealable and handleable.
All right, we have time for one last question. Let's take the experimentalist, and then I will open exception for you. Huh?
How does universality come into this? I mean, at no point have you discussed this. Well, it comes back in a way to the symmetries are broken, but the symmetries of a fluctuating order just doesn't seem to be important.
It's very important.
So where does that universality enter?
Yeah, for example, if I tell you my boson is a Kramers incoherent valley boson, then it tells me which superconductor I'm getting. It happens to be a specific orbital, valleys, triplet, mini valley, singlet, so the quantum numbers are all matter. I just was very generous with these details in this talk. So all of this matters, but if you look at the superconducting state, I'm looking at here at a single component superconducting order parameter. It may be sick because it has to deal with this non-quasi-particleness, but it's still just a scalar U1 particle. right? A charged scalar particle, and therefore that's what it is. If I wanted to do the same thing for a multi-component superconductor, it would have additional flavor indices, it could have all kinds of structure internally and so forth. I just looked at the simplest version of this one, and I think I'm also ready to do other things in my life than only this. So this was just to get an understanding of what the holographic aspect is, and I think that's why we focused on these simpler versions. Mm-hmm.
Last question. Is there a way to get a black hole without temperature, or the entropy? Oh, there is.
Rice-Nordström black hole is a charged object that at 0 temperature has a black hole.
So the entropy comes from where?
Well, first of all, once you are in this, this is a related question that we've just had. In this specific case, we have a 0-point entropy in this ADS2, which is the outer boundary. So if you have a system that has charge, your T equals 0, you're in finite dimension, you get what goes under the name of a Rice-Nordström black hole. That black hole solution, in its near horizon limit, maps onto this ADS2. Yes, it has a finite entropy, and that's why these SYK models also have a finite entropy.
All right. On that note, let's thank Professor Schmalian one more time.